Welcome back to data mining. In this module, we will talk about classification with decision trees. First, we will define what a decision tree is, and then we will look at how a decision tree makes its decisions. Lastly, we will look at how different data types function in decision trees. Let's get started. So why do we need decision trees? Well, when we humans make decisions, we typically identify the options that are available to us, and then we evaluate these options based on the criteria that are important to us. Let's take a look at an example decision tree. Here, the basic question is, does it move? Then the options for our decisions are no and yes. So if it does not move, the follow-up question is, should it move? If it does not move and it should not move, no problem. If it does not move, but it should move, we do something about it. Similarly, on our other branch, does it move? Yes. We then ask the same subset question, should it move? If it should move and it is moving, no problem. If it's moving and it should not move, then we apply duct tape. So this decision tree has worked because we have split our data set recursively. First by does it move, and then our second set is with should it move. That is the subset that we have built from the split that we have then split further until our termination criterion has been reached, which was either duct tape, no problem, or WD-40. Most decision trees work for classification and regression, so they're called cart or classification and regression trees. To give a theoretical definition, a decision tree is a non-parametric machine learning modeling technique for regression and classification problems then. A decision tree, we're seeing another one here to the left, makes sequential hierarchical decisions about the outcome variable, which is what we're seeing here on the leaf level, based on predictor data. So hierarchical here means that our model is defined by a series of questions. We're seeing those in the ovals here that lead to a class label. Here our class label is whether the credit applicant receives a loan or whether she is denied a loan. It is non-parametric, meaning that we're not making any assumptions of the data, but that we're looking at the actual data that we have, at the actual observations. And we can set this up as a classification tree, what you're seeing here. Here we have our class being loan or no loan. This is with a categorical class attribute, but it can also be set up as a regression tree in which our output is continuous. So how does a machine build a decision tree? Well, let's build one by hand and we'll see. We're going to consider this data set here that consists of 4 input attributes: age, income, student, and credit rating. And we're interested to see in what combination these are good predictors for our output attribute or our class attribute, which is bias computer. Bias computer is either no or yes, so binary. Our question is age by itself a good predictor for bias computer? Well, let's see. Our first age group is the under or equal to 30 group. That's these 5 rows here. And if we look at the bias computer output, we're seeing that age less than 30 or equal to 30, bias computer is no in the first 2. Then we have no in number 3. So far, the relationship is very clean and clear. But in the last 2 here, we're seeing yes. So we have 3 no's, 2 yeses. That is not a very clean and clear relationship. Let's move on to our next age group, the 31s through 40s. And we're seeing here we have 2 rows in our data set, and our output in this case here is Okay, it's yes for buys computer. That is a very clean and clear relationship. We like that. Our next group is the over 40s. Those are these 4 rows here. And our output here is, let's see, over 40, yes, yes. Up, there's a no here, so we also know we need to ask further questions. So the only group for which age is a good predictor for bias computer is, in fact, our 31 through 40s. And for our other group, namely the less than or equal to 30 and the over 40s, age by itself is not a good predictor for bias computer. We need to ask more questions. We need the other attributes to help us make a decision about our less than 30 and over 40 age groups. Let's first consider our under or equal to 30 age group. We know that these are the outcomes for bias computer. Now let's take a look at income and see if income will help us make a clean and clear decision about who buys a computer and who doesn't. We're seeing here income being high and age under and equal to 30. Bias computer, no, that's all really good, but we're seeing here where income is medium, bias computer, no, income is low, bias computer, yes, that'll work. But here we see age less than 30 and income medium, bias computer, yes, that's different from the no up here. So this tells us that we need to keep looking. Let's look at credit rating then. Age less than 30 and credit rating fair, bias computer, no, that might work. Age less than 30 and credit rating excellent, bias computer, no, that will work. So let's see here, age less than 30 and credit rating fair, bias computer, no, that's just like the first one that we've seen, that's good. And age less than 30 and credit rating fair, bias computer, yes, that's not going to work. And we're seeing here excellent led us to a no up here. And at the bottom we see excellent leads us to yes down here. So credit rating also not a very good predictor category. Now let's take a look at student. We're seeing if age is less or equal than 30 and student equals no, we're seeing that bias computer is clearly no. But if student is yes, then bias computer is a yes. That means that age in combination with the student status is a good predictor for bias computer for the age of less than 30 branch of our decision tree. Now let's see how the data behaves for the over 40 branch of our decision tree. We see here our bias computer output is yes, yes, no, and yes. So we have 3 out of 4. How about age in combination with income? We're seeing over 40 and low here leads us to a yes, but over 40 and low in our third row here leads us to a no. So income, definitely not a good predictor. What about being a student? We were lucky with that before. Age over 40 and no leads us to bias computer, yes. Age over 40 and yes leads us to bias computer and yes. Age over 40 and yes, bias computer, no. So also not a good predictor. Let's see if we're luckier with credit rating. Age over 40 and credit rating being fair, that leads us to a yes in 3 out of 3 cases. Very good. And age over 40 and credit rating excellent leads us to a no, which is also a very clean and clear example. So clearly, age in combination with credit rating is a very good predictor for the over 40 branch of our decision tree. And at this point, we have reached all of our labels on the leaf levels, and we're done with our decision tree. Now, the data type in our class attribute does influence how our decision tree makes its partitions. So, for example, we could have a categorical attribute as our class attribute, and then we would have a discrete partitioning scenario, which we're seeing here with our color and our income example. If A is continuous, we're looking at a regression tree, and then we're looking for split points. These split points are automatically calculated, which is what we're seeing here with income. Or if A is binary, let's say buys computer yes or no, then we're looking at a simple yes or no split as a partitioning scenario in our decision tree. All right, let's summarize. Our basic decision tree assumes that at the start, all training examples are at the root, that the class attributes are categorical. If they are continuous, we're looking at a regression tree. Our algorithm partitions our training set recursively into smaller subsets as the tree is being built, and that is based on selected split attributes. These split attributes or test attributes are selected based on a heuristic or a statistical measure. So when do we stop partitioning? We stop when all the samples for a given node belong to the same class, or when there's no remaining attributes for further partitioning. In that case, we need to employ majority voting for classifying the leaf, or if there are no samples left. So really the big decision that we have to make in a decision tree is which attribute to pick as the split point for our next tree branch. And that brings us to the end of our classification with decision trees module. You have learned how to explain what a decision tree is. We have looked at how a decision tree makes its decisions based on the attributes that it picks to split. And we have considered how different data types work in decision trees. Thank you very much for watching, and I look forward to seeing you again in a future module.